Hello everyone, today we will start numerical methods unit 8 where we discuss numerical integration. So in this unit basically we start with trapezoidal rule, then we see how we can improve trapezoidal rule using some Romberg integration. So first of all, what is integral? Integral actually is the area under the curve. So for example, if you have a function like this f of x, then the limit between a and b is actually represents the area. Now the idea in numerical integration is to replace a complicated function or tabular data with an approximating functions that is easy to integrate. So for example here, if we can replace a function as a polynomial, it's very easy to calculate. So for example, in case of polynomial, we can use integration to calculate it with limits a and b. Now, not all functions are integrable. For example, if we have this example, here it's not possible to integrate it fully. So we need some approximation of an integral in that case. So what we can do here is that this is area of the under the curve. So we can approximate it if we use a straight line between a and b. So we use that slope and calculate the area. This will give us a better approximation. So if we use only single straight line here, so we can use for same, because in single straight line we have more error because a lot of areas left not be covered. For example, here a lot of areas left. Now we use here 1, 2, 3 segments, so this will give much better results. So but we have to use more segments here. So using 3 segments we get better approximation. So similarly, instead of segments, if we use function here, that will approximate this one, that give more, but still we have error. So this means that the approximation method, when you use any method using single line or multiple line or a function, you still have a approximation of the original area under the curve. So here we use the parabola. Now we have another differentiation that we have closed and open loop integration formula. For example, if your endpoints is included, we call it as closed loop, integration formula. So if it is open, we call it open integration formula. Now we will start with the trapezoidal rule. So the idea is in numerical integration is to replace complicated function or tabular data with an approximation function that is easy to integrate. So for example, here we replace it using some polynomial. Now trapezoidal rule, first order polynomial are used. So we just approximate this function only with first 2 terms here. So we call it as first order polynomial. So what we normally do is that we approximate this function using only first 2 terms. Now if we have a function like this, we can use a single segment to approximate it. But in this function, if you see, if we try to calculate this area, it is type A trapezoidal. So we will come up some formula of the area that we can use to calculate this area using single line. So what we do actually, we know that this is slope actually, and that slope is calculated based on the line of this function time the difference, because this difference gives you this vertical line, okay, and this is the horizontal. Horizontal is difference between a and b, and vertical line is the difference of the function at f of b minus function f of a. So this is the slope. We want to write a equation of the line, so we have a slope times x minus a is here from where equations start, x variable start from a, plus f of a, which is the original value of the function. So this is the way we can write the equation Now we want to integrate between these points. So what we do actually, as we approximate using this polynomial, we do the integration for this one. So when we do that, we just rewrite it, because x is the dependent variable with dx and other values are constant, so we take constant one side remaining with x. So we continue with that, and now then we apply the limits. So we come up a formula that is a compact formula. So this is a very compact formula. So if we look at this formula, it based on the difference between these two points, so we call it width. And if we look at, this is a one height and this is another height of that trapezoidal, so we take the average of these heights. So we come up a very simple formula for single line segment, that we have to take the average of the height times the width is the area actually. Now geometrically, the trapezoidal rule is equivalent to approximating the area of trapezoid under the straight line connecting f of a and f of b. So this is the area, we use this to represent this. So the idea is very simple. So we have a width and we have two different heights, so we take the average of the height time width. So we use the basic formula of the area to calculate the integration here. Now is width times the average height. So we have width is given to us b minus a, and height is in terms of function values. So we come up with this approximation with single line segment, and we use this to calculate the area. Now the thing is, we have this f of b from the function values, and we can calculate it. Now error of the trapezoidal, as we know that we actually do the approximation, so we may have error. So how to calculate that error here? Now in actual situation we have no foreknowledge of the true value, so therefore an approximation error is estimated. So how we estimate it? When we employ the integral under a straight line segment to approximate the integral under a curve, we obviously can occur an error that may be substantial. So to estimate for the truncation error of the single application of trapezoidal rule based on Taylor series is, so if you remember, this was the error that is based on minus 1 by 12 second derivative times b minus a cube. Now to obtain the estimate, second order derivative over the interval can be computed by differentiating the original function twice, where zeta lies somewhere in the interval a and b. Now what is zeta actually? So to solve that problem, what we do actually, we do an example and see how we can accommodate this. We can accommodate zeta using the average integral. So for example, if a question is asked us to calculate the trapezoidal rule to numerically integrate the given system from a and b, so a, b is given to us. So next thing is, note that exact value is also given to us. So it is 1.640533 here. Now function is this one, so we have to actually calculate the integration using trapezoidal rule. So in trapezoidal rule, basically we need two values. We already know a and b. Now we need two function values at 0 and at b. So when we do that, we just plug the formula to calculate the integration. So this is the formula that we need to apply. So after calculating value at a and b, put in the formula, so we come up with the solution. Now look here, this solution is 0.1728, but original value is 1, so this is a huge error occurred. So this is using single line. Now the error is 1.467733, so it's a big error. Okay, now if we look at the percentage true error, relative error, so percentage relative error is 89.5%. so this means that lot of part is not covered, area part is not covered using this approximation. So further analyze how is this actually happened here. So for example, this is the whole area. Okay, so this error has more part than compared the area that is covered with this approximation technique. So reason for this large error is evident from the graphical depiction that the area under the straight line neglects a significant portion of the integral above the line. So therefore an approximation error estimate is required. So how we do the approximation estimate? So we have this formula. So let's see. So now we have same question. Now we have to apply the formula. So in that formula we need the second derivative of this. So what we did here, we take the second derivative and plug the value here. Now the problem is that what is the value of zeta here? So let's see, we use the average integral, average value of second derivative. So how we do that? We take integration from 0 to 0.8 and divided by the difference. So this gives us the average integral value that represent our zeta here at second derivative. Plug the value. Now true error is 2.56 here. Sorry, true not approximated error using this error estimation. Thus we denote that the errors are approximated using the notation E of A rather than exact T. So okay, so we have to represent this is an approximation error, not the original error. Okay. In trapezoidal rule, to improve the accuracy we can use multiple application trapezoidal rule. So in that case, one way to improve the accuracy is to divide the integral interval from A to B into a number of segments and apply the method to each segment. So for example, here we just use 2 segments here. We can increase these number of segments. When we increase the segments, we cover more area. So we have 3 segments here. Similarly, we can go up to 4 segments. So this is one of the way we can use to improve the area using trapezoidal rule. So we can go up to 5 segments. So here, look here, we cover most of the part under the curve between x0 and x5. Multiple application trapezoidal rule. If the interval AB is partitioned into n segments, for example, if we have AB and we divide into equal segments, n segments, for example. So if this is a function and we can divide from A to B, but the important point is that these segments widths must be the same. Now if we want to calculate any segment area, is follow from the trapezoidal rule from the single segment. So we just take the height average times the width. So if we sum all these trapezoid segments, we actually get the value of the area under the curve between A and B. Okay, in this method we actually applied the linearity property of the integration, where we can have different segments can be summed up to give the result. So here what we did here, we actually divide the whole function into n partitions, but making that each partition width is same, and we call it h. So because there are n, so we can calculate h using b minus a divided by n. Okay, now in this so this is the linear property of the integration. So we start from x0 to x1, then x1 to x2, and so on. So here you see x1 is coming 2 times, similarly x2, but only x0 and xn actually coming once in this formulation. So this is very important. So when we apply integration on each segment, so here x0, x1, so x0 is coming 1, x1, then x1 again coming between x1 and x2, and so on. So we just plug the formula here. Now after this, what we did actually, we just take h by 2 as a common, and we have single entry for x0 and xn. We just write it separately, but 2 times x1, x2, and up to x of n minus 1, we take the summation 2 times. So this is the formula that we come up when we divide into n segments. Okay, now we can rewrite, because we know that h by 2 is actually equal to b minus a, which is the width, times 2n, and this is x naught xn. So this is the basically the formula that give us a result when we use n segments, okay, to represent the integral. Now the average derivative that we can use for this one is based on, because we use this second derivative to calculate the approximation error, so we can use this based on take the derivatives for each one and then divide by and take the average of that. So we can come up with this approximation error formulation for n segments. Okay, now this is what we can use for multiple segments. Let's see an example how we can solve this. So use two segment trapezoidal rule to estimate the integral of the given system between a and b. Do also estimate the error. So now we know the exact solution. Now this is the same example as we did in previous cases. So we see how we can improve the result by including more segments. So here we have to use two segments. So h is b minus a. So b is available, a is available, n is number of segments is 2. So we can find easily h. H is 0.4 in this case. Now f of 0 is the original segment, that is 0.2. Similarly, the last one is 0.8, but in between we have 0.4. So these are the three values, function values that we use. So because there's only one segment and that comes two times, so we have to apply the formula. So formula is this, that b minus a times the initial one, 2 times of mid one, and the last one divided by 2. So we just plug this formula and we come up, this solution is 1.08688. Okay, now if you look at the error here, so based on the exact value, true error is relative true error is 34.9%, is much better with the single segment where we have 89% is the absolute true error. So if we want to use it for calculating the approximation error, so what we do here is that we need to take the average integral here. So we apply this formula. So we look here 0 to 0.8 because this is between this, and we take the second derivative and we come up with minus 60, and then we plug here because n is 2 here. Now the approximation error is much improved. In this case is 0.64. Now if we increase the number of segments, okay, so here we make a table, and when we increase the segment, we of course we have different values of h. So as you increase the segment, your h value decreases, so that we see in column 2. Now if we look at the integration, for first one is this, and when we increase it, the number of segments, we get this results, and you look, it's very interesting that relative true error is decreasing as you increasing the number of segments. So this is a big improvement with including more segment in trapezoidal rule. Now error order is of h square, so it is double all the time. So means that doubling the number of segments quarter the error, because when we double the segment, we actually reduce the h as well, so that will help us to get better result. Now we will look at some Romberg integration that is similar that we discuss in difference, where we use some extrapolation. So we will, Richardson, it is similar to that one. So let's see how we can apply this here. Now Romberg integration is one technique that is designed to attain efficient numerical integrals of functions. So here it is quite similar to trapezoidal rule that we discussed, in sense that it is based on successive application of trapezoidal rule. But the trapezoidal rule with an interval h gives error of h square. Thus, we can combine two trapezoidal rules with an interval of h and h by 2 to get better estimates. So the idea here is that we use combination to reduce this order h square to h4 and so on. Okay, so we call it at Richardson extrapolation. These methods use two estimate of an integral to compute the third one. So the idea is to more accuracy. If you use two estimates, you do have better accuracy. So how we do that? So we combine trapezoidal rule for h square to yield a new estimate of h4. So how we do that? We need to calculate the integration using trapezoidal for original value of h1 and then divide by 2. So then we apply this formula that we see in Richardson extrapolation. Then if we apply this formula, we have h4. Okay. If we further want to reduce this, then we have to use this h2 with h4. Okay, then we reach up to h6. But in that case, instead of 4, you have to go for 16 and 15. So 16 by 15 values of the integral and so on. So this is the way we can improve further. If you want to improve it further, then you have to move to further value down, and then you can achieve up to big O of h hat. That includes 64. So this is the way we can improve the Romans integration. So where IM and IL are the more and less accurate estimates. So to clarify this, for example, if you have same question, if we want to apply Romans integration and we want to have accuracy of big O of h4, so we have to use the first formula of Romans integration. We know the exact value, so same function is used as we used previously. So what we did here, so previously we know that when we use one segment, so we have 0.8 and this is the integral value and this is the approximation. So for Romans we have to divide this. So when we divide by 2, we come up with this segment. So we use two segment here and we know the result. So we use these results and plug the formula. We come up with the Romans integration. So this is for 0.8 is for this one, h1. Similarly for 0.4 is this one. So we already know the value. We just plug the value here. Now when we do that, we come up with solution of 1.367467. So the true value, you look here, relative error is decrease. It is 16.6. Look here, we have 34 here, but here we reduce up to 16.6. So this is much improvement. If we go to estimate of the segment 2 and 4, if we use in our formula, then it will further reduce it, and the true value is up to 1%. So this means that this formula actually improves a lot. There's an extrapolation technique. So how we use that? We use these two values for h squared to come up with h4. Similarly, we use next two values to come up second. So then we use this two to come up h6 and so on. So this is the way we apply this formula to calculate the Romans integration. Now, so previously we know that these two are values for Roman integration, so we can apply this to further decrease it up to h6. So then we have to use this formula of h16. Now we use these two values to calculate this. So when we do that, it is 1.640533. So this is exactly the correct answer to this number of significant figures, that is 7. Okay, so but if you have more significant figures, of course you do have error. So because this is based on h6, right? So that's why you are getting the same result in this case. Now if we do another one, and if you go for h hat, so we have to go for 16 formula. So if you write the formula 64, okay, so you do that, and this is what we have. So this is the similar table that we have in previous Richardson interpolation. So we have n is there, so we have h by 2, and so on. Okay, so we call it 0 0, so this is based on h square. Now the next one is based on h4, then h6, h8. So we use these two to come up with this result. Okay, similarly we use these two and come up this result, these two with this, then we use these two to come up this and these two, and we know the last term is because of h8 has more accuracy. Okay, now this is the first column using trapezoidal method. You can use it by just dividing the h by 2 all the time. You get the result for first column. Second column is Roman's method. Okay, so if we apply to our example, so this what we get much, because for same significant figure we get the same result. Result is not changing afterwards. Okay, now so this is the way we calculated. We use these to come up with this result, then we use these to come up the second result, then we use us to come up this. So this is the way we come up the result for H8. So now this is the question and ask you to apply the Romberg's integration by yourself. You can try this. Just pause the video and try this. So what we do, first of all, we have to calculate for H1, that is R00, then H by 2, that is R10. Then we have to go for, this is the generalized formula that we can use to calculate the next values. Okay, now after using this we can calculate R11, R110 and so on. Okay, now similarly RH1 by 4. So after calculating all the values 2 by 1 using this generalized formula R22, we can come up with this table, and we have to put values from this formula resulted into this table if we want to calculate up to H6. Okay, so this is the result that we are achieving with this formula for this particular example. Okay, now that's it for integration part. We discuss trapezoidal rule and Romberg's integration methods. In trapezoidal rule we discuss single and multiple segments method, and in Romberg's integration we actually introduce some interpolation techniques to improve the result. Thank you for listening. Bye.